Hey everyone, and welcome. Today we're diving deep into the world of LLMs, just like we did last week. However, we're going to talk about how they actually work and some things behind them. We're going to continue based off last week, so welcome back to, I believe this is week 5. So we're going to look at LLMs just like GPT-3, which are basically the brains behind many modern AI applications. We'll be breaking down the key concepts of transformers and attention mechanisms, the technology that powers these models. This is going to be based on the paper from 2017 by Google called Attention is All You Need. So let's get into it. What are transformers? Transformers, at their core, are designed to take in text and predict the next word. The input text is broken down into tokens, which are usually words or parts of words. This is known as the tokenization process. Each token is then converted into a high-dimensional vector called an embedding. This is done using an embedding algorithm, which maps each token to a corresponding vector in a high-dimensional space. So, why do we do this? There's many reasons why. Number one, LLMs can't really understand words simply, and you can correlate this to how a computer will not understand Python code, but the Python code is then compiled into zeros and ones, which the computer can understand, right? So we always have to remember these computers can only understand binary. Similarly, uh, LLMs can only understand numbers. And this is essentially what the tokenization process does. So the key idea here is that directions in this high dimensional space correspond to semantic meaning. For example, there might be a gender direction where adding a vector in that direction transforms a masculine noun into a feminine one. There might also be directions representing tense, plurality, or other semantic features. This allows the model to capture relationships between words based on their meaning, and to perform operations on the embeddings that correspond to meaningful operations on the word themselves. So, this essentially gives us the different definitions of certain words. For example, I might actually have this example later, but we're going to consider the word bank and see why this is useful. So, the initial embedding is just a lookup table and actually doesn't consider the context of a word. So, given this example, let's consider the word bank. It has different meanings in the phrases, I went to the bank to deposit a check, and the boat drifted towards the riverbank. Initially, the embedding for bank would be the same in both cases. Transformers adjust embeddings to incorporate richer contextual meaning. This allows them to understand the nuances of language and to generate more accurate and coherent text. So, our attention mechanism. This is where the attention mechanism comes in. It allows the model to move information from one embedding to another, even if they are far apart in the text. For example, in the sentence, the cat, which was sitting on the windowsill, was black. The attention mechanism would allow the model to connect the word cat with the word black, even though they are separated by several other words. This is done by assigning a weight to each word in the sentence, based on its relevance to the current word being processed. The weights are then used to create a weighted sum of the embeddings for all the words in the sentence, which is then used to update the embedding for the current word. Essentially, this just gives us context of an entire sentence based on individual words. So let's look at it step by step through an example. Let's consider the phrase, a fluffy blue creature roamed the verdant forest. So for the queries, keys, and values, each word generates a query vector, which represents a question, a key vector, which represents an answer to a question, and a value vector, which represents information to be passed. These vectors are created by multiplying the word embeddings by weighted matrices, WQ, WK, and WV, each for queries, keys, and values, which are learned during training. The weight matrices are different for each attention head, allowing the model to capture different types of relationships between words. The model calculates a score for each word pair by taking the dot product of their query and key vectors. The dot product is a measure of similarity between two vectors. This score indicates how much each word should attend to other words. Words with high attention scores are considered to be more relevant to each other. Then there is softmax. Softmax is a function to create attention weights, so these scores are normalized using this function, which essentially puts them between 0 and 1 and sum up to 1 for each column. The softmax function ensures that the attention weights are all positive and that they sum to 1, which allows them to be interpreted as probabilities. And as for value aggregation, each value vector is multiplied by its corresponding attention weight, and the results are summed up for each word. This creates a weighted sum of the value vectors where the weights are determined by the attention scores. This weighted sum is then added to the original word embedding, updating it with contextual information. This allows the model to incorporate information from other words in the sentence into the embedding of the current word, again, giving it more semantic analysis, essentially, for the model. So, during training, the model predicts the next token for each subsequence in an input. To prevent later words from influencing earlier ones, which essentially would give away the answer, a masking is applied. This involves setting the attention scores for the future tokens to negative infinity before applying softmax, effectively zeroing them out. This ensures that the model can only attend to words that have already been seen and that it cannot use information from future words to predict the current word. Now let's look at multi-headed attention. Transformers use multiple attention heads. Each head had its own set of key, query, and value, just like we talked about. Each head learns to capture different types of relationships between words. For example, one head might focus on grammatical relationships, like adjectives modifying nouns. Another head might focus on broader semantic relationships, like wizard and Harry Potter. The outputs of all attention heads are concatenated and then linearly transformed to produce the final output of the attention block. This allows the model to combine information from multiple attention heads, which can capture different types of relationships between words. Now, in addition to attention blocks, transformers can also contain multi-layer perceptions, otherwise known as MLPs. Research suggests that MLPs are responsible for storing factual knowledge. They consist of two matrix multiplications with a nonlinear activation function, also known as ReLU, something we learned in the earlier weeks. In between, the ReLU function introduces nonlinearity into the model, which allows it to learn more complex relationships between words. Now, how do MLPs store facts? Let's imagine how an MLP could store the fact that Michael Jordan plays basketball. Okay, assume there are directions in the embedding space representing Michael and Jordan and basketball. This means there are specific vectors in the embedding space that correspond to these concepts. The input vector is multiplied by a matrix that transforms it into a higher dimensional space. This allows the model to create new features that are not present in the original embedding space. One row of this matrix might be Michael plus Jordan direction. This means that this row of the matrix will be activated when the input vector contains both Michael and Jordan concepts. A bias vector is added with a value of -1 in this component, Michael plus Jordan. This bias vector is used to adjust the output of the matrix multiplication. You might notice there are some similarities from when we talked about neural networks a couple weeks back about weights and biases. And just know that all of those concepts apply here because this is essentially a neural network, but a fairly large one. Now, a ReLU function is applied, which sets all negative values to 0. This creates a clean AND gate where the output is 1 only if both Michael and Jordan are present. This result is multiplied by another matrix that projects it back to the embedding space. This allows the model to combine the new features that were created in that higher dimensional space with the original features in the embedding space. The column of this matrix corresponding to the Michael Jordan neuron might be the basketball direction. This means that this column of the matrix will be activated when the input vector contains the Michael Jordan concept. A bias vector is then added. This bias vector is used to adjust the output of the matrix multiplication. And so as an output, if the input vector encodes Michael Jordan, the MLP will add the basketball direction to it. This means that the output vector will contain information about both Michael Jordan and basketball. So let's quickly talk about superposition and why interpretation is hard. The idea of superposition suggests that individual neurons rarely represent single, clean features. Instead, features might be represented by combinations of neurons. This is because high-dimensional spaces can store exponentially more nearly perpendicular vectors than truly perpendicular ones. Pretty much, this just means that while a single neuron might have slightly different information from another one, all we care about is the sum of all those neurons and from layers and all that we talked about from the previous weeks. Now, every large language model has to go under training, just like how a neural net does. So the model is trained to predict the next token in a sequence. Just like neural networks like we learned earlier, there is a cost function that measures the difference between the model's prediction and the actual next token. The model's parameters are adjusted using gradient descent to minimize that cost function to ensure there's as much, accuracy for that model in its training. And finally, we have parallelization, the key to efficiency, and truly what this paper really revolutionized for the large language models and what we have today. Transformers were found to be highly parallelizable, meaning that their computations can be run simultaneously on GPUs. And graphics processing units are really good at math, and matrix math at that, so no wonder LLMs, became a great option. This is a major reason for their success, as it allowed them to scale up to enormous sizes. And you wonder why NVIDIA was worth $3 trillion at some point. Every large language model was being trained on their GPUs simply because they had CUDA and great architecture to train them on. So that kind of does it for this week. Thank you for listening to this presentation or watching. Next week, we'll be talking more about LLMs and neural networks. So see you then. Thank you.